Hello everyone, welcome to this live session of our course Fundamentals of Nuclear Power Generation. We had live sessions earlier which were actually done on YouTube, and I was really happy with the response that I got during that particular live session, as there are questions asked before the session through the Google Sheet, and also there are several questions which was asked during the live session itself through the YouTube link. And I hope we are going to have the same response for this session as well. Yeah, Harish, good to see you again. See you as well. I hope some more participants or some more students will be soon joining this particular session so that we can have an introduction. And this being a meeting conducted in MS Teams, I question you are asking and the time it takes to reach me, which will not be here, and we can have a better communication maybe. Regarding the course, we are towards the end of the course at this moment, and therefore, I think we are presently in week number 11. So we can easily have a discussion about different topics at almost the entire content of the course. The later topics like those we are getting covered in this week number 11, and also. Okay, it's week 10. Fine. Actually, the content of week 11 we have just uploaded, which will be available to you very soon. So week 10 is done. The contents of week number 11, etc., are maybe descriptive of nature. Descriptive nature, like we shall be talking about the nuclear safety and security protocols. We shall be talking about a few other things like biological aspects of radiation, etc. But the topics that we have covered so far, those are quite a bit mathematical or analytical in nature. Like since our previous session, we had discussions on the nuclear reactor controls. We had discussions about the breeder reactions or breeder reactors. We had discussion about the fusion reactions. So I hope you have got an idea about many of those topics. And if you have any query, I shall be happy to respond. So unfortunately, there are no questions asked in the Google Sheet, which I checked just before coming here. But if anyone has still any questions, I can see at least a couple of students are already here. If you have any question, you can directly ask me here. And by the time some questions comes to my way, I may like to give a brief roundup of whatever we have done in this particular course. Like we started from very basics, the atomic structure. Whenever we are talking about nuclear energy, of course, we have to start a discussion on the nucleus, nucleus of any particular atom. There is not too much interest, or it is hardly relevant, the electronic structure or the electrons which are rotating in the orbit. Rather, we are focused more on the electrons, or sorry, more on the nucleus or solely on the nucleons. Yeah, of course, nucleons are also not the most fundamental particle. Rather, we can break them even more. But this being just the first course on nuclear power generation, I have not gone to the fundamental particles. In more advanced level courses, you can get introduced to the topics like bosons and fermions. We can talk about the quarks and leptons, which actually forms like that. There are two different kinds of quarks, up type and down type. And the up type, two up type and one down type quarks forms a proton, whereas one up type and two down type quarks together form the neutron. But those are beyond the scope for this course, so we have restricted ourselves to nucleons only. Then we have discussed about the way of characterizing any particular nucleus in terms of the atomic number and mass number. Then we have talked about the isotopes. Isotopes are just the nucleus or nuclei of the same element which are having same atomic number, because atomic number is a characteristic of any element, but they have different mass number because the number of neutrons are different in different nuclei, and therefore we can have different kinds of isotopes. Almost every element that are available in nature have multiple isotopes. There are certain elements for which one of the isotope is so much dominant that we hardly experience or hardly can sense the presence of the other isotopes. Like a very common example can be oxygen. There can be several isotopes of oxygen, but the 8O16, which is the most common isotope that is so much prevalent, that is the oxygen that you get in nature, in atmosphere, almost 99.7% of that is 8O16. So you can virtually neglect the presence of other isotopes, but truly speaking, oxygen can have isotopes starting from 8O13 to 8O18. and even a few others also synthetically produced in the laboratories. Or like something very relevant to our course, uranium. The uranium is a metal which we get from mines. The natural uranium ore that we get, 99.3% approximately of that is uranium 238, and only about 0.6 odd percent is uranium 235. And therefore, at least whenever you are talking about the chemical properties, you almost can neglect the chemical properties of uranium 235. And also, I must mention that the chemical properties are not dependent at all on the number of neutrons or as such the mass number. They are governed by the atomic number. So, from chemical properties point of view, from chemical reactions point of view, the all isotopes are same. But from nuclear property point of view, they can be substantially different. And also there are certain other elements which can have multiple isotopes present in very high quantities, like copper. I forgot the exact mass numbers, but copper, I guess copper has two isotopes of 63 and 65 are their respective mass numbers. And well, I am again not sure about the numbers, but I think copper 63, that is about 70% of the natural copper ore is copper 63, whereas remaining 30% or approximately 30% is copper 65. So both are quite substantially available in nature. Now, once we have talked about the isotope, we then subsequently talked about the stability of a nucleus. As the several nuclei of the same element can have different number of neutrons. Some of them can be stable, some of them can be unstable. And you now know that there are several ways we can characterize the stability of an isotope, or at least there are several thumb rules. And the most important thumb rule is in terms of the binding energy. The binding energy is associated with the mass defect, the difference between the actual mass of an isotope and the combined mass of its constituents. The combined mass is always higher, and the difference is what we call the mass defect, and corresponding energy is the binding energy. And the binding energy is the amount of energy which is required to overcome the electrostatic repulsive forces of all the protons, which are restricted within a very small volume. And because of this binding energy only, they can stay there because it is a very strong nuclear force. And binding energy per nucleon gives us an idea, some kind of overall idea, or as per some thumb rule, gives us an idea about the stability of an isotope. The highest value of binding energy per nucleon among the natural isotopes we get is around 8.7 mega electron volt, which corresponds to mass number in the range of 56 to 60 or 62. Some isotopes of iron and nickel have that level of binding energy per nucleon, and they are the most stable isotopes. And isotopes which are having much higher mass number and having low binding energy per nucleon, they try to participate in some kind of nuclear reactions during which they break to produce lighter isotopes, so that each of the resultant isotope have higher value of binding energy per nucleon. Accordingly, we get the concept of fission. Whereas the isotopes which are very light, their option is to combine with another one, and accordingly they have a resultant isotope which is heavier in mass number and also higher in terms of binding energy per nucleon. And accordingly you get the concept of fusion. Now, fusion is restricted mostly to the experimental cases or experimental reactors. And so in this course we have predominantly talked about fission reaction for power production purposes at least. So we have discussed about the concept of radioactivity. There can be natural radioactivity as well as the induced radioactivity. Natural radioactivity talks about the spontaneous decay of the unstable isotopes, during which it can emit some kind of particle, like it can emit alpha particle or beta positive or beta negative particle, or maybe some other kind of radioactive emission, I can say. So in certain rare cases that can eject neutrons, etc. And subsequently it produces another nucleus, another isotope, which is more stable, or at least tries to produce something more stable. That is natural radioactivity. But from fission reaction point of view, you are more interested in the artificial or induced radioactivity, where we start with an isotope which is generally stable, or even if it is unstable, it may have a very low decay rate, like uranium 235. It is naturally radioactive, but its decay rate is very slow. Its half-life is very large. Therefore, if we are depending only on the natural decay of uranium 235 for production or of subsequent or sufficient amount of power, we shall never be able to achieve it. So we go for the artificial or induced radioactivity, where we break a stable isotope or maybe something which is naturally unstable but has a very low decay rate by striking it with a neutron. Of why neutron, that I have explained in the course, because neutron is electrically neutral and also sufficiently heavy. So when a neutron strikes a nucleus, the nucleus breaks and we have the fission reaction, because the products of that particular nuclear reaction generally have mass lesser than the reactants, and the corresponding mass defect leads to large amount of energy. Typically, fission of a single uranium-235 isotope or nucleus can give approximately about 200 mega electron volt of energy, which is quite large. And once you multiply that with huge number of neutron isotopes that can be present even in the smallest possible volume, then we are talking about a very large amount of energy. But of course, whenever a neutron strikes a nucleus, it is not mandatory for the fission to happen. We can have other kinds of reactions as well. In some cases, we can have just a plain non-fission capture reaction. In some cases, we can have collision or scattering kind of reactions. And what reaction is going to take place, that depends on two factors. One is the kinetic energy level of the neutron, and the other is the nucleus alone, or the nucleus itself. Like there can be certain nucleus which can have fission cross section, which may not have fission cross section alone. Like if you take 8O16, whatever may be the kinetic energy of the neutron, if any neutron strikes a 8O16 nucleus, there is never going to have any kind of fission, because it has zero fission cross section. Only certain nuclei can have fission cross section, non-zero fission cross section, so they can act as fuel during such kind of fission reactions. But there are other elements which have very important role to play inside the reactor. Like certain isotopes can have very high scattering cross section, so they are used as moderator in order to convert high kinetic energy neutron to a low kinetic energy neutron. Harish, I am coming to your question soon. So why we need to convert or reduce the kinetic energy of a neutron? Because the fission cross section is generally very high only with low kinetic energy neutron. When the kinetic energy of the neutron is high, when you are talking about fast neutrons, the fission cross section generally is very, very low. So you need to have moderator inside reactor which reduces the kinetic energy of the neutron and therefore facilitates the fission reaction. Now we have also talked about what I can say. We have also talked about the chain reaction. Means the fission products that are formed, they are also generally radioactive in nature, naturally radioactive, and so they can have their own decay. During that decay, some neutron can get produced, which are called delayed neutrons, whereas the neutrons which are produced directly from fission, they are called prompt neutrons. Delayed neutrons have very important role in controlling the nuclear reactor. We had a detailed mathematical analysis to see how the presence of solely prompt neutron affects the neutron density or time rate of change of neutron density, and how the presence of very small amount of delayed neutrons can improve the situation by helping a much slower rate of increase in the neutron density. We also talked about some external factors of controlling the rate of reaction, like the control rod, chemical sheen, etc. We have discussed in detail. Then we have talked about the reactors, thermal reactors, different kind of thermal reactors, pressurized water reactor, boiling water reactor, pressurized heavy water reactor. Then we have talked about the breeder reactors in the next module. Now here comes a question that Harish is asking. Right, sorry, it's Harsh, it's not Harish. Okay, Harsh, the question that you are asking is between chain reaction and breeder reaction. Now chain reaction is the use of neutrons, or rather the use of the neutrons which are produced during a fission to activate another fission reaction. That is, if we initiate a fission reaction, during every fission reaction we have neutrons produced. Typically 2 to 3 neutrons are produced. On an average 2.42 number of neutrons are produced during fission of every single uranium-235 isotope. and generally you can have 1 to 5 number of neutrons produced. These neutrons are all fast neutrons, so they go through the moderation process to become slow neutron, and then each of these neutrons can strike another uranium-235 nucleus and can initiate fission further. Therefore, we need to control the rate of reaction. If we want to have a steady rate of reaction, then whatever number of neutrons produced, we have to absorb or remove some of them from the system, so that the number of neutrons causing fission in every generation remains the same. So that's what we refer as the chain reaction. Neutrons produced during one fission is causing the next fission, and the neutrons produced during the second stage of fission causing the third stage of fission, etc. And if we can control the rate of reaction, then we shall be getting a stable chain. That is, the number of reactions in every stage remains the same. That is chain reaction. Breeding reaction is something else. Breeding reaction refers to, here we know that there are two kinds of materials we can talk about, fertile and fissile. Fissile means whenever a neutron strikes that, a thermal neutron or low energy neutron strikes that can undergo fission reaction, because that has some value of fission cross section, some significant value of fission cross section, like uranium-235, uranium-233, thorium-233, plutonium-239 or 241. These are examples of fissile isotope. Whenever a thermal neutron strikes these isotopes or these nuclei, there is a possibility of having fission reaction. So the nucleus which can undergo fission reaction, even when they are being struck by a thermal neutron, we term them as fissile. Like uranium-238 generally has very low fission cross section, and therefore if we strike that by a thermal neutron, we are not expected to get fission. So it is not a fissile material. Whereas the fertile materials are one which they don't undergo fission because they don't have fission cross section. But whenever a neutron strikes them, maybe a thermal neutron, then what happens? They capture the neutron, and after capturing, they undergo some kind of decay of their own, generally 2 stages of beta decay, during which they cause, or rather they produce, a fissile isotope. That's why you may be getting confused with chain reaction, but it's not. It's more like a radioactive chain, not a chain reaction. Chain reaction term is used when the neutrons are getting utilized in every step. Neutron produced from step 1 is getting utilized in step 2, and produced during step 2 is getting utilized in step 3. But we can also have the radioactive decay chain, whereas we start with some some unstable isotope which decays, beta decay or gamma radiation or alpha decay, whatever, produces the second isotope, which is also unstable. That decays, produces a third isotope, and this way we keep on going till we reach some kind of stable isotope. That is what we call chain reaction. Now, that is a radioactive chain. Now, breeding reaction involves such kind of radioactive chain, but there is no role of neutron. Means, like if we take the example of uranium-238, which is a good example of a fertile isotope. Uranium-238 captures one neutron, produces uranium-239. Now, of course, we are initiating the process with a neutron, but in the product side, there is no neutron present. Rather, we have uranium-239. And uranium-239 goes through 2 stages of beta decay. So uranium has an atomic number of 92. During the first stage of beta decay, it produces atomic number of 93, and again during the second stage, it produces atomic number of 94. So after 2 stages of beta decay, we have 94 Pu239. Mass number remains the same during beta decay, but atomic number increases by 1. So 92 uranium 238 captures one neutron, produces 92 U239, and then through 2 stages of beta decay, it gets converted to Pu 94 Pu239. There is no further neutron produced, and this 94 Pu239 is a fissile isotope, so it can participate in fission reaction. So the breeding reaction refers to, we start with a fertile isotope, it captures a neutron, and through some kind of natural radioactive decay produces a fissile isotope. That's what we refer as a breeding reaction. But it's a radioactive chain, you are correct, but it's not a chain reaction as such, or nuclear chain reaction which we get during fission reaction, because no neutrons are getting produced in any stage. Rather, we are converting one fertile isotope to a fissile isotope. I hope your doubt is clear in this case. Is there true breeder reactor possible or only pseudo breeder? I'm not sure what you are asking. Pseudo breeder means true breeder reactors are definitely possible. Breeder reactors are there. In India, we have very rich storage of thorium, thorium 232. Thorium 232, thorium has an atomic number of 90. 90 Th232 is very commonly present in India, and it has India has largest reserve of thorium 232, but it is not a fissile isotope. So in our new generation's breeder reactors, we are using this breeding reaction. Thorium 232 is capturing one neutron and getting converted to 90 Th233, and then it is going through two stages of beta decay. So 90 becomes 91, and then 91 becomes 92. After two stages of beta decay, it produces 92 U233. So thorium 232, after capturing one neutron, getting converted to thorium 233, and thorium 233 after two stages of beta decay getting converted to uranium 233, which is a fissile isotope. And so that can undergo fission, and that's actually a big part of Indian nuclear power program, where we are starting with fission. Sorry, we are starting with thorium, and which is a fissile isotope, and converting. We are starting with thorium 232, which is a fertile isotope, and converting that to uranium 233, which is a fissile isotope. And actual breeder reactors are always there. Now, I also got one question about the moderator being used as a reflector. Now, what is the purpose of a reflector? Purpose of a reflector is to scatter or reflect the neutrons which are trying to escape the core back to the reactor. So the reflector needs to be something which has very high scattering cross section, and the most common material that you can get inside the reactor itself, which has high scattering cross section, are the moderating material like ordinary water or heavy water are very good examples. They have very high scattering cross section, and so whatever like they can act as moderator, they can also act as reflector. I am not saying that the moderator itself acts as a reflector, but the same material can be used as moderator as well as reflector. So you can think about this way. We can think about this moderator is something that in which you have the fuel rods immersed. The fuel rods are immersed in moderator, so that whenever a neutron is trying to reach a fuel, it has to pass through the moderator. During this process, it goes through the moderation, and it is able to reach the fuel as thermal neutrons. But the reflector that may be around this moderator fuel combination, that maybe the entire what I can say, the entire reactor is immersed in a big pool of water, which will act as a reflector, reflecting the escaping neutrons back to the core. So reflector materials and moderator materials are same, and therefore a material which is an excellent moderator can also act as an excellent reflector. So similar materials are used, but not necessarily moderator itself is used as a reflector. Now I just got a question about the fleet mode. I am not sure about fleet mode. This is a term that is new to me. I have not heard about this. I have to search, truly speaking. I have to read about this fleet mode in nuclear reactor. If any other question is there, I shall be happy to respond. Towards the end of the course, we have also briefly discussed about the fusion reaction. Fusion, yeah, Maninder has raised down. You can ask. Okay, then I don't know. I will check it out. I'll check out the news about the fleet reactor. I'll check it out. Of course, it's a new term. There may be something part of the planning, long-term planning. I'll check it out. Maninder, you can write your question in the chat box. I can see the chat box. Like towards the end of the course, we have in one of the later modules, we have talked about the fusion reactor. So very briefly, we have talked about that. Common examples involve the isotopes of hydrogen as well as some isotopes of helium. But I have also expressed what are the challenges there, because fusion reactors requires a very large magnetic field, very high temperature, and those are real challenge, at least at this moment, even from material point of view, things are definitely improving. But once we have better control on this, maybe. Okay, delayed neutron fraction and beta fraction. I am coming there. So once we get a better control about the conditions leading to fusion reaction, definitely fusion reactors can become commercialized or licensed. And you know that fusion is the reaction which goes on inside the star. It has huge potential as energy producing technology, and if we can master that, of course we can what I can say, we can have a big solution for the energy crisis of the world. Now, delayed neutron fraction and beta fraction are virtually same thing. Only in certain limited cases they can be different, but mostly we generally consider the beta fraction itself as the delayed neutron fraction. At this moment, unless you are dealing with a real life data, there is no need of making a differentiation between them. You can just consider both as the fraction of delayed neutrons among the total neutrons. That is a new density of delayed neutrons divided by the density of prompt neutrons plus density of delayed neutrons. You can treat that way itself. There is no need to. I may have mentioned, I can't remember, but only in special cases, certain limited cases, we may have some difference. At this moment, there is no need to go for any kind of differentiation. I think the entire mathematical deduction that I have done involving delayed neutrons, there I have used the beta fraction only. Beta fraction officially is defined in using the concentration of the delayed neutron precursors, because very rarely some delayed neutron precursors can produce more than one neutrons. Then we can have some difference between the two, but generally we can, that is such a rare phenomenon, we can almost assume that every delayed neutron precursor isotope or nucleus can produce just a single neutron. So whatever is the concentration of the delayed neutron precursor, the same is the concentration of the delayed neutrons. The difference will appear only if there is substantial presence of some precursor producing more than one neutrons, which is very, very rare phenomenon. And that's why you don't need to make any kind of differentiation between delayed neutron fraction and beta fraction. Beta fraction is defined, I repeat, in terms of the concentration of delayed neutron precursors, but you can just take that same as the fraction of delayed neutrons. I just got one question here which I have missed. I know something came on the screen, but let me just check if I can get this again.
Professor Basu, can you hear me?
Yes.
Professor Basu, my name is Maninder Singh.
Can you please switch on the camera? Then it will be good to have the interaction.
Sir, unfortunately, give me a few minutes. I'm having some struggle with my laptop and internet connection. So
okay, then you can carry on.
Sorry, sir. Sorry. Sir, I have 2-3 queries in my mind.
Some queries are trying to respond.
Yeah, some queries are related to my assessments, my quiz assessments. And I have been writing in the forum that my quiz has not been correctly assessed.
We have got, just sorry to interrupt, but not from you, from others also have got some questions. All of those will be taken care of. Sometimes we may not be able to respond to that, or database at your end may not be getting updated, but be assured that we are taking care of any such mistakes. There are certain assignment problems which got evaluated wrongly or with the we have rechecked all of them, or we shall be rechecking them again if that something is not corrected yet, and that will be taken care of.
Okay, sir. Then I have a second question. This is regarding enrichment of fuel assemblies.
Okay.
Do we in PWR reactors, do we when we are loading the fuel, do we load the fuel with same concentration, or concentration is different of different fuel assemblies?
Yeah, that can be different. That can be different.
Okay.
Yes.
Okay.
Because like the neutron density inside the reactor may not be same everywhere. There can be a spatial distribution. Generally, neutron density around the core can be higher and neutron density towards the edges can be lower sometimes. And to
Okay.
compensate for that, if we are going for a more careful design, sometimes we use fuels having more greater level of enrichment towards the edges, and fuel
Okay.
having lesser levels of enrichment, or maybe natural fuel itself towards the core, so that we can
Okay.
have almost uniform power profile.
Okay. Okay. Okay.
Not mandatory, but it is done in certain reactors.
Okay. Sir, another request I wanted to make, if it is possible, it will be my humble request that if we can have another interactive session like this over Teams, in which the participants can have a classroom experience, I would be very grateful. And I can come with some queries, and then we can. I have actually many such queries, so that when I raise a query and when you explain, then I have some counter questions also, instantaneous counter questions. So would
Yeah.
be grateful if you can have such
I
interaction.
shall be always happy to have kind of thing, because online mode always we are always handicapped in a way. A live classroom is the best thing to have. I will forward this. This is not in my hand. I will forward this request to our office, and if they can arrange something, I shall be available to respond, or
Yes,
available to attend such a session. Definitely.
yes. I will put this in the forum tonight,
You
so
please
that
put in the forum. We will forward this to our office, to the NPTEL office or our local office, and if they can arrange a session, I shall be very happy to be there.
yeah, today's experience also is very great. Unfortunately, I'm not on laptop. It would have been better if I would have been at the laptop. But if we have one more such session in within a week, I would be very grateful on
Uh,
Teams.
Let me see. I will just what I told. I will forward to our office,
Yeah.
and if they can arrange, I have no issue with that.
Okay. Thank you. Thank you, sir. Thank you.
Thank you. Because I have a question from you, is it possible to have direct nuclear energy for small scale uses like in submarine aircrafts? At least in nuclear powered submarines are already there for years. Aircrafts, I am not sure whether they are using nuclear energy or not, but definitely in submarines, nuclear submarines are there. You can search over internet to get some information about them. So small scale uses, and not only small scale, actually not only small scale in submarines kind of thing. Rather, there's a concept of small nuclear reactors, portable nuclear reactors, which has also come up. Not very popular yet from commercial point of view, but you can say we are talking about some very isolated location, some islands or something where you need to have some source of energy, and there is no other kind of source available. Or maybe you are there's a big research team traveling to some deserted location, and they need to have some source of energy, say for 6 months or something. Then the concept of this portable nuclear reactor, so you can have some very small reactor. You can easily get an idea that the size of a nuclear reactor core is much smaller compared to the size of an equivalent power equivalent boiler, thermal boiler. So if we can have a portable nuclear reactor, then it can be carried with the team and it can be placed there, or maybe some isolated location, maybe just to serve a small village, just like a biofuel based reactor kind of thing. And that concept of portable reactors are already there, and some companies are commercially producing that also, but still not that popular, at least in our countries. It is still not there, but it is possibility. Aircraft carriers,
Sir,
okay, aircraft carriers particularly use the nuclear weapons. I don't know they are running on nuclear fuels or not, actually. Yeah, Maninder.
sir, here I would like to share an experience
Yeah,
of,
please.
not experience, a knowledge of the rovers that we are sending on moons and Mars.
Yes,
They are also nuclear powered. So very
yes,
small
correct,
reactor is
correct.
put there so that they have sustainable power for
Yes,
while in their life when they're at that remote location.
yes, correct. It's a good example. I forgot to mention about that, but it's very correct. Depending upon the lifespan for which they are designing this, they put equivalent or proper amount of fuel so that it can run for that many years, whatever is the planned thing.
Hello,
Yeah,
hello, Professor Basu.
yeah, Harsh.
Yeah, yes, actually, I have one query in the control mechanism that in that we saw that if the reactor is less than or equal to the beta factor, so that is actually the necessary condition for a controlled reaction, right? But then if
Desirable,
we are
I should say desirable condition.
Okay, but then my query was that if we are using the control rods in the reactor, so I don't think that this is we should take into consideration or something like that, because we are
No.
using the control rods.
See, there are the mathematical thing that you are referring to. There are two parts. Firstly, one analysis was done considering only prompt neutrons, correct? Neglecting the presence of delayed neutrons. Now, if delayed neutrons are not there in the analysis, you have seen that prompt neutrons are not prompt neutrons provide very little time for operator to act. Like within just a few seconds, there will be an exponential increase in the neutron density if for some reason reactivity becomes non-zero. Now, if delayed neutrons are there, then the analysis that you are referring to, there as long as the reactivity is less than the beta fraction, then the exponential factor is negative, and therefore reactor itself will be able to subside such kind of fluttering, you can say. It will come back to the normal stage. But of course, that is something that is a self-control kind of thing that we are talking about. But if that is not there, we can't we can't rely solely on that. We need to have external mechanisms, and for as per that external mechanisms, we need to have controllers and all other kind of assemblies. Now that comparison between rho and beta that you are referring to, that is natural. We don't need to talk about any kind of external mechanism in relation with that. But suppose when you are starting a reactor, your reactor is cold, you are starting the reactor, then you need to have very high rate of reactivity, because you want your power production to start from zero and go to the rated capacity within some specified period of time, maybe a few hours or over a day or two. And during that period, you want to start with a high reactivity and gradually adjust the reactivity such that once you reach the rated capacity, reactivity has come down to zero. And that kind of fine tuning is possible only through external means. There the control rods comes into play. Or the opposite, if you want to shut down the reactor, I may have mentioned the term scram. Scram is for
Yes,
accidental shutdown, but even during the normal shutdown also, your reactor is operating fine with a reactivity of 0, multiplication factor of 1, and getting a consistent power production. Now you want to shut it down for maintenance purpose or for something. Then what you have to do? Then you have to use the control rods or similar mechanisms such that your reactivity reduces. And you have to reduce the reactivity sequentially such that over a planned period of time or a specified period of time, it becomes almost zero. So that the power production reduces. Scram is something for accidental purpose where we suddenly wants to reduce the reactivity to zero or some extremely low value so that the reactor stops operation. So those kind of planned operations, or even during emergency or accidental situations also, we need to have control rod kind of mechanisms to take care of that. Whereas the delayed neutron fraction that you are referring to, that is a natural control. The natural control over the reactivity that we get because of the presence of delayed neutrons in the system. As long as your rho is less than beta, actually you don't need to do anything during normal operation. Like for uranium, beta is I think 0.0065. So only 0.65% of the total neutrons are delayed neutrons with uranium 235. Now, if there is suppose 0.1 or 0.2% increase in the reactivity during operation, then it will automatically be taken care of by that delayed neutrons, and that fluttering, it will quickly come back, or over a period of time it will come back to again the zero value, zero reactivity. But if the change in reactivity something is like 0.7 or percent or even more, then you need to act. The operator has to act.
Okay, sir.
Professor Basu,
Yes.
I have a question that when we have loaded the reactor, at that point in time, the chain reaction has not started. So how
Yes.
do we trigger the chain reaction? How do we get the first neutron to trigger the reaction?
Okay. We have to supply the first neutron from outside. It is just think about starting our car or starting a bike. Like to start it, we have to kick that, right? In an
Okay,
IC engine, using a kick, or by a car using a self starter, we have to start it. And once it starts, it self start. It's means self operated.
sustains.
So it is similar. We have to we have to supply the first neutron from outside. We have to trigger the reaction somehow.
Okay.
And after that, it will take care of. or
Okay,
at a
okay.
control rate or something.
Okay.
So external
Understand.
neutrons will be required to start with, but again, just to start with. Like once you have started your bike, you don't need to use that kick again or the starter switch. Very
Okay.
similar.
So the it starts with some source of neutrons.
Yes.
We not some high energy particle, proton or something from a small cyclotron or something. It comes and hits and causes some disturbance in the nuclei,
Yeah.
and the reaction starts.
Yeah, there are certain devices. I actually forgot the exact composition, but there are certain materials which are very neutron rich as well. So sometimes we use this kind of isotopes. We put them inside the reactor or certain location to have a large neutron flux to start with, and then we remove that. Somewhat
Okay.
this way. Exactly how it happens inside the reactor, that I also am not in a position to tell, because I don't have that real experience inside the reactor to do. But there are certain neutron rich materials available which are commercially used to trigger the neutron or trigger the chain reaction for this.
Okay, doc. Okay, thank you.
Any other question from anyone?
Hello.
Yeah, Harsh.
So for that chain reaction, that first neutron that we use, so what type of neutron is actually it is? Is that a prompt neutron, direct neutron, thermal neutron, or some special neutron we use, or
See,
some
whatever source you are going to use, that is generally going to be a fast neutron, high energy neutron. So the moderation process will still be there.
okay, sir.
And it's not possible that you can produce a neutron with a specific level of kinetic energy. So moderation process is there. And always we are starting with a fast neutron, whether it is coming from some external source or whether it is getting produced from a fission. You have a fast neutron, you already have the moderator inside the reactor. So you don't need to bother about that moderation process. That will
Okay,
always
sir.
happen. And reactors are designed such that the neutron will go through the moderation phase before it can reach the fuel. So that's a part to the designer, how they will design this.
Okay, sir.
Okay, any question, please?
Also, sir, one more thing that in this course, that whatever we are learning, we have just seen the pure application of the heat transfer actually. As I am right now, I'm in third year, I am doing mechanical engineering. So as far I have seen the application of the heat transfer and the other mechanical engineering subjects. So is there any application of research oriented subjects like particle physics or quantum mechanics, something like that? Means in this nuclear physics field.
Yeah, nuclear physics is a very big thing, right? So the entire quantum physics is involved to explain the procedure of nuclear reactions, like exactly how the reactors are designed, how to control the neutron life cycle. These are all associated with the quantum physics. So this is a huge area of research, of course. Heat transfer is only the external part. Means once the energy is produced from the reactor, then you can have heat transfer. That energy will be taken by the coolant and you will be having a Rankine cycle outside, etc. for power production. But the energy production part, that entire thing is particle physics, or you can say the quantum physics. Even I am also a mechanical engineer, and so my knowledge is also not there about that particular thing. I am also seeing more from engineering point of view. The area of research in quantum physics, or like we do works related to more the thermal hydraulics. It means how to utilize that energy, how to work on the safety of a reactor, etc. from heat transfer point of view. If there is some accidental scenario, how to remove the energy additionally. Like you must have heard about that the Fukushima accident in 2010.
Yes, sir.
Now, Fukushima was a big accident in nuclear power station, but actually there are a couple of things. Firstly, Fukushima was a very old design, well past its deadline, And so there were not too much passive cooling mechanism or passive safety mechanism installed there. And because of the tsunami, now the power went off, and as there was no power, so there was nothing to run the coolant pump. So there was no coolant circulation to take the energy from the what I can say, the reactor core. But nuclear reaction is not something like you can just switch on or switch off. So it will take certain time to die down, and therefore it still continued to produce energy. And as there was nothing to take that energy, so because of the overheating, it melted and we had the radiation coming outside, etc. That is a very putting in a very crude way this. Now the modern nuclear reactor designs which are coming up, they all have the passive safety mechanisms. Like even if there is malfunctioning of the pump, then there will be some kind of natural circulation based systems which will work based on the density difference and will keep on taking the energy, etc. So this this kind of thermal hydraulic things are very important for research as well.
Okay, sir.
Professor Basu?
Yes, yes.
I have a question about the efficiency of PWR and BWR. My thinking is that PWR should be more efficient versus BWR. When I compare the two, just a minute, Professor.
Yes.
Sorry, sir. My child was making a noise in the background.
Okay, no.
So we have a BWR and we have a PWR. So when I look at the Rankine cycle and we see the Rankine cycle with with superheat, the Rankine cycles with superheat are more efficient versus the Rankine cycles which do not have superheat. So my thinking is that PWR should be more efficient because the cycle is under pressure, and so there is superheat degree of superheat available, and due to this degree of superheat, the PWR should be more efficient versus BWR. Wanted to have your views on this, Professor Basu.
No, that way actually in PWR, you know that we are working at high pressure, so that the temperature
And high
of
temperature.
in temperature of the fluid always remains less than the saturation temperature. It is not allowed to change phase. It is always pressurized water, liquid water. So whereas in BWR it is like normal power stations, it can be where, but it is boiling water. Yes, you are correct. Means the option of superheating, you can say, like even in PWRs also, it is not that the pressurized water that gets the energy that itself is directly utilized for power production. We may have a external secondary cycle also, where the fluid will take the energy from this water, and then it will go to a boiler for this, instead of directly using the water which is circulating there. And also if we want to use a superheating something, sometimes we can use an external device as well for increasing the heat in a temperature, rather temperature even further for this. So it is difficult to make any conclusion about which one will be more efficient from that point of view as such. You are correct with your view that PWR works at a higher temperature level inside the reactor. So if we think about Carnot cycle, then that should give you higher efficiency. Whereas BWR, the temperature level is lower in BWR.
Right. So from that, there was a question in the quiz related to that. So I was scratching my head that, and just to give you some background, Professor Basu.
Yes.
I have been interested in nuclear since, say, 2010. I have about 35 years of industry experience. I'm basically a power plant engineer, and I work for an American multinational. But my interest is very much there in nuclear power. So that is why I have been studying on my own. And in my own study, I had concluded that PWR should be more efficient versus BWR. The reason being that the Carnot efficiency of PWR should be higher.
Temperature level is higher, correct.
Temperature level is higher. Yes. Otherwise, and also on in BWR, we are putting wet steam in the steam turbine. And when you put a wet steam in the steam turbine, the design, the steam turbines do not work very efficiently. Whereas in PWR, it's you start with a dry steam, and towards the last stages of the blading, you have wet steam. So my overall conclusion was maybe uh, pressurized water reactors should be more efficient versus boiling water reactors.
Yeah, firstly, it's fascinating to know about your interest. Despite spending so many years in the industries, you are still interested in academics, learning new things. So it's really motivating for us as well. That
No, motivating for me, sir.
now about the thing, that's what I am saying. Of course, theoretically, PWR should have more higher efficiency, or should offer higher efficiency because of higher temperature. But practically speaking, it's difficult to say. BWRs are more challenging, that is for sure. BWRs have issues with control also. Like one
Yes.
big challenge with BWR is that we are using water as moderator as well. Now, when the fluid or the water itself starts boiling, now we say that water is an excellent moderator, but that is liquid water, not the vapor. Now, as the water starts boiling, the vapor starts to appear inside the reactor core. That vapor doesn't offer the moderation effect. And if the
Oh,
moderation is not happening, the power production rate or reaction rate also will die down.
oh, very
So
interesting.
that is also something that is to be taken care of. But
Uh,
still, both kinds of plants are very commonly used. Both have their advantages and disadvantages from operation point of view, and that's why theoretically you are very correct. PWR has higher efficiency.
Sir, another question which has always been lingering in my mind is that when we are using water as a moderator, uh,
Yes.
after this water, which is being once used as moderator, does it remain radioactive, or the
No,
water itself never becomes radioactive?
no, it doesn't become radioactive because it's a more collision reaction, right? There is no change in the
Okay,
nuclear structure. It
okay,
has higher energy level, maybe. It can,
okay,
but again, you are comparing the mass of one neutron and the nucleus being mass being higher, there is not significant change in its kinetic energy as such for this.
okay.
Is the neutron loses kinetic energy and theoretically the nucleus gains that kinetic energy, but as its mass is higher, so that gain may be lesser. So
Okay.
its kinetic energy increases, but it's not radioactive. Nucleus,
Uh,
it remains H2O or D2O only.
okay. Sir, I have one more question.
Or
Maybe
sorry, I
we'll
should say it remains plain hydrogen or deuterium only. But there is no change in the nucleus structure.
understand that part, sir. So I have one more question, sir. Maybe we'll be studying that during the later modules or towards the end of the session. But let me put the question here. If we are studying, you can explain me that you can tell us that it will be discussed later. Then we can leave it there. The inside the reactor, we have fuel. Other than fuel, we have cadmium rods, boron rods, other stainless steel components, reactor pressure vessel is there. So the material which is normally not radioactive, or which is non-fissile material, non-fertile material, like stainless steel, uh, does it become at any point radioactive when after the fuel has been utilized, and I take out, say, there's a crane inside the reactor which lowers the fuel or pulls out the fuel assemblies, so that gets exposed to some amount of radioactivity. So that those components which is are like stainless steel. So when we take them out, uh, do they carry any radioactivity in the future, or they don't carry radioactivity?
No, there are two things. Firstly, stainless steel, we can be very safe with that because iron, hardly any of the isotopes of iron has any radioactive nature. These are very, very stable. Like again, we can go back to very beginning of the course, binding energy per nucleon.
Right.
So all the isotopes of iron, all the common isotopes of iron have very high binding energy per nucleon and they are not naturally radioactive. So even if
Okay.
they capture some neutron, they will get converted to their heavier isotope, but it will be stable mostly. Now, there are certain isotopes like you mentioned about the boron rods, etc., or cadmium rods, which are used in control rods. They capture neutron. Like boron 10 is the very common isotope that is used for control rod. Now, when boron 10, 5b10, that captures one neutron, it becomes 5b11. That is radioactive. But
Okay.
that actually has very fast decay rate. Very promptly it decays to produce lithium and helium. It decays to produce lithium and helium, and they are very stable, and the decay rate is very high. So as soon as the boron captures a neutron, almost within seconds, it loses that radioactive nature for this, because it gets converted to lithium.
Okay.
And therefore, that's why I'm coming to the other part of your question. Means even if there are materials which capture some neutron or something and becomes radioactive, but we have to be mindful about the decay rate. Most of them generally have very low decay rate, sorry, very fast decay rate. So they decay quickly. And once all of them has decayed and finally reached to some stable isotope, we generally don't need to bother about their radioactive nature.
Okay, so that means when we are talking of nuclear waste, we are essentially talking of the fuel that we have put, uranium and enriched
Yeah.
uranium that we have put. That is
Fuel can be
that's
there. Also, there can be the fission fragments.
yes,
Fission
yes, yes,
fragments
yes.
can also have very long half-life. Some of the fission
Right, right, right,
fragments. So
right,
they
right,
can
right, right.
also survive for years.
Yes, 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 yes. Understand
But
that part.
other materials like the control materials, structural materials, generally don't need to bother about too much.
Okay,
Or even
okay.
moderator also.
Okay. Understand. Also, sir, want to share with the group here and with you also. The
Yes.
company for whom I work, we have an ownership of a company called NewScale. NewScale is designing a small modular reactor SMR.
Yeah, I
Uh,
know that. Yes.
so
Yes.
we are producing the 77 megawatts electric is being produced by one module. So we are trying to sell that sell that reactors. So I'm the salesman of that technology in Indonesia. I do not have access to, because I'm an Indian national, I do not have access to the technical elements of that. But I'm being allowed only very superficial access, but I'm trying to sell this technology to Indonesian government.
Okay. That's New Skill. I know the name New Skill. I forgot actually. Somewhere we met with some representative of your company also in one of the sessions where we had discussions on nuclear energy. And there I heard about their modular reactors as well. But 77 megawatt is quite high actually.
Actually, very high. It
Yes.
started with 45 megawatt electric. So as they continue to refine thermal hydraulics, they did not change the design of the fundamental design of the core, but slowly, because of modifications, it ultimately was revised to 50, then it was revised to 60, and now it has been revised to 77.
77 is very high. So
Very high.
yes.
And my expectation is, sir, it would somewhere come to about 100 megawatts, is my feeling.
Okay.
We have obtained the NRC, Regulatory Commission of the US. We have obtained their approval for 60 megawatts. Now we have given our applications to upgrade it to 77 megawatts. And also would like to share with the group here is that that my company is manufacturing only the reactor part, the steam turbines, cooling towers, condensers, other electrical components you can buy from shelf from any other company. For example, BHEL can manufacture it, or other manufacturers, Doosan, or anyone. You can buy the steam turbine from off the shelf, marry it. The concept is that the nuclear design is necessary only for the reactor.
Correct.
Other than that, ASME for others, the sections of ASME are not applicable. You can design the other part in accordance to the ASME. ASME got several sections. One section is related to nuclear, other section is related to power. So you can use power for the design of rest of the power plant. Only for the reactor, you need to design it in accordance to nuclear code, which is not typical of the power plants that India has purchased or any other which are commercially available at this point in time.
Okay. It's really nice to hear. You can write in the group also, maybe in the portal for this.
Yes, I would write, and I would send some details to you also, Professor,
Yeah,
on
there
this.
I shall be happy to communicate also.
It's
Yes.
very interesting, very interesting. The footprint is
Yes.
also very small. It's amazing technology, and if you would desire, if you have interest, when we have next session for industry, we can invite you to join our session, in
Sure.
which
I shall be happy to join.
the real experts, technical experts, make a presentation there, not like me.
Okay, thanks to everyone. We have to wrap up the session now because there'll be another session for some other course for this. But if anyone has any further query, please write to us. We shall be happy to respond for this also. And thanks to Mr. Maninder in special. Yes.
Thank you, Professor, for your time.
Yeah. Thanks a lot.